Hello everybody, thanks for joining me once again. We're looking at question 8 on the 2005 Euclid contest. So it's a completely written question. We've still got an A and a B part to deal with. So 8A. A function is defined by, we have a piecewise defined function, f of x is equal to, well, it's a constant 4 if x is less than negative 4. It's negative x if x is between negative 4 and 5 inclusive. And it's negative 5 if x is equal to, if x is greater than 5. On the grid in the answer booklet, I don't have one, sketch the graph g of x is equal to square root of 25 minus, okay, those aren't absolute values, although it wouldn't matter if they were, 25 minus f of x squared. State the shape of each portion of the graph. Okay, state the shape. Well, g of x is going to depend on f of x, which depends exactly where x is. So what I'm going to do is I'm first going to write out g of x in piecewise form, just like they've written out f of x in piecewise form. And I'm going to build g of x up very slowly. First I'm going to say, what is f squared of x if x is less than negative 4, if x is between negative 4 and 5, that sort of thing. Then I'm going to say, well, what's 25 minus this f of x squared? And then I'm going to finally say g of x is, well, what if we square root it? What happens when x is less than negative 4? That sort of stuff. All right, and then we're gonna sketch it, and I'm betting just based off of the way g is set up. I'm noticing f has some constants. I bet g will have some constants, but I'm also thinking that we're gonna see portions of a semicircle or things like that. But that's just a cursory glance. Let's actually get to it and work out what g of x is. So, fresh piece of paper, obviously. So let's get our f of x, we'll just copy it down. Negative 4 if x is less than negative 4. Negative x if x is between negative 4 and 5. And then, what was it? Negative 5, right? Yeah. Negative 5 if x is greater than 5. Okay. So from there we can say, well, f of x all squared. I just need to square these results. So when x is less than negative 4, f of x is negative 4, so negative 4 squared is 16. Negative x squared is just x squared. And negative 5 squared is just 25. So we can very quickly build up what f of x squared is. So 25 minus f of x squared. So it's 25 minus 16, or 9. It's 25 minus x squared. And it's 25 minus 25, so that's 0. And now our last one, g of x, is root of the whole thing. So square root of 9. Now we have to be careful. This symbol, square root, very specifically means you take the positive value. So we got a 3 here. We'll deal with only positive values for 25 minus x squared, all square rooted. And then 0 square rooted is just 0. Okay, so now I have my g of x. I can probably fit a sketch up here. We're only going to need the positive axis, or the positive side of the y-axis. So we'll sketch it somewhat carefully. So we'll put -4 here, maybe -3, -2, -1, 1, 2, 3, 4, 5, and then we're going to keep going. So here's our y-axes. What are we going to need? Well, we're going to need things between 3 and x can be 0, in which case then we're going to need to go all the way up to 5. So 1, 2, 3, 4, 5. Okay. So what have we got? Well, g is 3 when it's, we'll use some color here. So it's 3 when it's 4 or less. Actually, we shouldn't have this blue circle filled in. It should be open for a moment because we don't know what actually happens at 4. From 5 onward, it's 0. And they asked us to describe these parts. I would say, constant horizontal line. And I would also say up here, constant horizontal line. Really nothing else I can do to describe those. It's the middle bit that's interesting. And now, root 25 minus x squared. If you haven't seen something like that before, you might be more familiar with it if we're graphing y equals g of x, which we are. You would say, well, then y is root 25 minus x squared. You could say y squared is 25 minus x squared, or you could then say x squared plus y squared is 25, which is 5 squared. And you might be a little more familiar with this. It's a circle of radius 5. Centered at 0, 0. And if you wanted to, because it is a written question, you could explain this, but I would say most people know root 25 minus x squared is going to be a semicircle of radius 5, centered at 0. So the phantom part of it, because we're only considering it between -4 and 5, is part of it there, and then it goes and reaches its maximum up here at 5, and it comes all the way down here again. So I would say part of semicircle. I wouldn't include this dashed line here, just because they might get confused as to you don't know what a graph is, but it's probably okay. Part of semicircle of radius 5, centered at 0, 0. Well, we don't really have to think about it, because we recognize root r squared minus x squared for the formula that it is. It's part of a semicircle. Okay, so there's our graph of y equals g of x. Wasn't particularly difficult, and we labeled every part, and I think that was it. Sketch the graph, fine. State the shape of each portion of the graph, constant horizontal lines, and parts of semicircles. We're good. So that's a part there, not particularly bad, although I wrote this paper in high school, and we didn't really do sketching a whole lot there, so kind of an out of left field question. Now, I admit, just looking at these circles, we're probably going to have to do some circle geometry. We didn't really do that a whole lot until maybe a little bit in grade 12 when I was going through. And so anyone saying, well, you shouldn't have sketching because it's not in the curriculum, you shouldn't have circle questions because it's not in the curriculum then either. But we have a lot of circle questions, so they're kind of expected. Sketching, that's more of a thing you might see on an old Descartes paper. Anyway. 8b. In the diagram, two circles are tangent to each other at point B. Fine. A straight line is drawn through B, cutting the two circles at A and C, as shown. Tangent lines are drawn to circles at A and C. Prove these two tangent lines are parallel. Okay. So I'm going to have to draw a copy. The picture here really is not selling the parallel to me, but that's okay. draw a picture, and there's points of tangency. I like usually connecting those up to centers of circles. We don't have a whole lot of information to go on. We have these two circles. We were not told anything about their radii or anything like that. So we'll see how well I can draw circles. So there's B in there. So they're tangent at B, so we draw a line through B. And it's just a straight line drawn through B. So it's not, doesn't connect up their centers or anything weird like that. Okay. So we get C and we get A here, and then we have lines of tangency, which I'm trying to draw properly. So I guess with mine they look parallel, but I mean my C1 should probably be a bit more slanted. All right. Now, these things here are points of tangency. No, I was going to say they got to give us right angles, but that's only if we connect up from the center, which we don't necessarily have. Okay. What are we going to do? I'm going to draw this one a little more slanty. Alright, so they tell us these things should be parallel. Well, these are points of tangency, so I'm going to connect them up to the center. So radius little r, we'll talk about that in a moment, or we'll say something about it. We'll connect this guy up to the center as well. So points of tangency do give us right angles. It's just a shame those right angles aren't necessarily at the line AC. Okay. Oh, and now let's call the other radius big R. So, what to do? What to do? If I could extend the line A through, let's call these centers big D and little d for the centers. If I could extend the line through AD down here till it hits, if I could guarantee that that is a right angle, then these guys would have to be parallel. So that's a thought. Is it a good thought is the question now. So my eye keeps looking at B, because we got to use B somehow. So I would draw the line tangent to both circles through B. Now eventually he's going to come up here and intersect. He's also going to come down here and intersect. And I get the feeling I might want to show that this angle up here is the same as this angle down here, because that can only happen with parallel lines. But is that good enough? We also would have a right angle there and a right angle here. Those are the points of tangency just fine there. What to do? What to do? What to do? What to do? Well, I'm going to enlarge the area around B just for a moment. I don't actually know that they're coming together. Actually, no, they do have to be straight through there, don't they? Yeah, so that also connects up their centers. So there is a way to connect up the centers, but that's not necessarily the line that we're working with going through B. So then that hits A and C, and so there's our B. So we can certainly connect up centers capital D and D through B. My picture does not show that in any meaningful way, but we can. It looks like D, my little d here is on the wrong side. So I'm going to move him so that he makes more sense. Okay. And when I do that, so I've connected that line up, is there a way to show that this gives us a right angle here? Because now my original thing is back in play. So I'm going to take away the right angle signs because they're sort of getting in my way. So I got sort of two methods on the go right now. One of them is, can we complete these right angles here, which obviously must be true if they are going to be parallel. The other thing I'm thinking about is this green angle is the same as this green angle. This green angle is the same as this green angle. And we got these ones are the same. So I'm wondering if I can somehow use that and some similar triangles to show what we've got going on. So for example, the double green angle and the single green angle must be a 90-degree angle. And our triple angle is also a 90-degree angle. I'm not seeing anything to do right now. And this is what's frustrating. I'm sure there's a connection here that I am missing. I just don't know what that would be. Let's call this angle up here alpha. So that's AC, or the line AC, and where it meets this tangent line. If I can show that this guy down here is also alpha, we'd be fine. So we've got alpha, we'll call this one beta, and so now this angle down here is gamma. So then this one's got to be, oops, gamma is spelled that way. So then that angle there has got to be gamma. And we got this double angle here is going to be the same as that double angle there, which is the same as this angle here, which is going to be the same as this angle here. And so gamma plus that, so this guy's got to be gamma as well. So there we go. That would give a proof. So now we've got to write it up. Okay, so what did I need? I needed that these two angles were the same. And we had them add up to 90. Alright. So I think we can do this. Alright, I don't know, let's change it to D and E so they're capital letters. Usually we want points to have capital letter names. Be the two centers. And P and Q... No, it's A and C, they already had names. Okay. So we'll redraw our picture here. We've got B, we've got E over here, we've got D, although it really doesn't matter what side D and E are on here, our proof will work, but one of them's on one side, one of them's got to be on the other side. We don't need to explain that. We're just drawing a picture. The math will work regardless of what side E would be on. Alright, so first thing first, connect DE. I'm color coding it in my proof right now. And then I might say something like let R and S be... we don't need to actually name the radii. Okay. And connect DA and EC. We'll make them red. Okay, since A and C are the points of tangency, we're going to need then DA and EC make right angles. With the tangent lines. Okay. So what do we want to say? So we got these right angles here. So make right angles. Here we go. It doesn't particularly look like it on the picture, but that's okay. Now, since DA equals DB, because they're radii, and EB equals EC, again, because they're radii. We see we have triangle DAB and triangle ECB are isosceles. So angle EBC is equal to angle ECB and angle what do I want to say here? Angle DBA is equal to angle DAB. Alright, I do think I need a couple other named points. So let's call this one X over here and Y. Let X and Y be points on the lines as shown. So then CAX is DAX plus DAB, which is 90 plus DAB, which is 90 plus DBA, which is 90 plus EBC, which is 90 plus ECB, which is ECY, plus ECB, which is equal to ACY. Now, the one thing I didn't prove right now is that this angle is equal to this angle. So we might need a little note somewhere. DBA is equal to EBC, as they are opposite angles of the intersection of DE and AC. There we go. And now finally, since CAX is equal to ACY, therefore AX is parallel to CY. And you might want a bit more of a sentence there, but there it is. So we showed this angle here is equal to this angle. Some call it the Z theorem, but it's perfectly fine. I've color-coded it all for you guys because it's a little involved with the diagram, but there it is. You might want to explain a few more things. Obviously, the little note I had to add down here should probably have been in the explanation ahead of time. And maybe you might want to be a little comfortable saying why D and E are opposite sides, but really it's because there's a line and we're going to have this in. B is the intersection point. So D and E will have to be on opposite sides of AC, and that means X and Y here are perfectly well chosen. So there's a little bit you could clean up, but I think it's all fine, and the major points are there. There's probably another way to do it with, as I said before, the tangent line through B. That might yield a nice result. But I liked it. It was certainly a challenge. I had to bust out parallel line techniques and things like that. But there we go. So we got 2 more questions on the contest. Question 9 I'll jump right into in the next video. Thank you guys as always for watching, and I'll see you next time.